Awesome. So thanks for coming. Thanks for coming back. I'm Matt Ahrens. I work at Delphix, and I'm going to be talking to you about performance of ZFS Send and Receive and some things I've done to improve it. So if you have been a faithful OpenZFS Developer Summit attendee, you might remember this talk from 5 years ago by my colleagues Paul and Dan about how send and receive performance is awesome. And they were talking in particular about incremental sends are way better than the competition because we're able to find all of the blocks that we need to send very quickly without having to look at all the metadata or look at all the files. So that's cool. And whether it's an incremental or a full send, we can get really good throughput. So more than 10 gigabits per second for both send and receive. So I don't know, why am I even here? Well, it turns out that's only true if you're using large blocks. If you're using smaller block sizes, then you get maybe a third of that performance. So you're nowhere near saturating your network. So why do we care about this? So I work at Delphix. In our product, we use ZFS to store databases. And databases store their data, record structured, typically in records of 8K. So to align with that, we're using ZFS, we're setting the ZFS record size property to 8K to match that. We get really good compression ratios with LZ4 ratios of about 2 to 3x. So the compressed block sizes are 3 or 4 kilobytes. And we found that, so you can use our product to do replication between Delphix engines to move your database data around. And you might have like a 10 gigabit or faster local network, or you might have Cloud Direct Connect, which we've seen customers have those up to about 5 gigabits per second. And we would like to be able to saturate that, but we can't. And the other wrinkle here is that a lot of the time, the majority of the data is just in one file system, so we can't take advantage of like running multiple sends in parallel. Why do you care about this? You might have the same kind of setup, or you might be using zvols, which default to the vol block size of 8K, or disk images where you want to have smaller record size settings as well. So my goal for this project was, we want to be able to do a ZFS send, pipe that over the network, pipe that into a ZFS receive on the other system, and ideally we want to like saturate either the network or the disk. Like some piece of hardware should be going full tilt, and we shouldn't be waiting for the software and the CPU. But unfortunately, that is the case today. So the goal that we set at the beginning of the project was to be able to saturate one of these 5 gigabit per second Cloud Direct Connect networks. And we want to be able to do it with an average compressed block size of 4 kilobytes, which means that we need to be processing 160,000 blocks every second, which means that we have about 6 microseconds to process each block, which is not very long. So this is just showing the same thing that I said, but in more detail. So the larger block sizes, like 32K and up, get really good performance, but then as you get down to these smaller ones, it's not that great. And the goal of the project is not necessarily to improve the performance of send and receive at these large block sizes, but just to make the graph a little bit smoother, bring the performance up specifically of 4K compressed block size. So I'm going to be talking a bit about like how we did this, and then I'll tell you about a few of the improvements that I made. I had to try like a lot of different things. So there's a lot of iteration. So when I'm iterating, basically what I'm doing is like looking at a flame graph, seeing what's using CPU, going and trying to find out, is this actually important? If I could get rid of this cost, like it seems like there's this cost in this particular code path. If I could get rid of that, how much would that improve send and receive? And that's a different question than actually like fixing it. So to give an example, like every time you instantiate a debuff, we need to allocate some memory and we need to do some space accounting to say like, okay, now there's this much amount of memory that ZFS is consuming for its internal data structures. There's probably like locks associated with that. So, maybe I see the locking is taking a long time. Rather than like breaking up the lock or doing something sophisticated, I was just like, okay, delete that code or comment out that code and see if we get better performance. If we do, then I can go back and implement a real solution. So I made lots of hacky changes that just that work for this narrow use case of send and receive, but wouldn't necessarily work for ZFS in general. So then I could come back towards the end of the project and evaluate like which of these will give us the most impact to performance for the least amount of effort. Right. So the test setup that I used was not the full-blown like product with databases and networks to the cloud. But I wanted to look at the performance of send and then receive separately because send and receive obviously they go together like peanut butter and jelly. You almost can't have one without the other. But under the hood, they're doing almost totally different things, right? Because send is getting data, receive is taking the data in and then writing it out. The code paths are very different. So things that might improve one don't necessarily improve the other. But I did want to capture the costs associated with the pipe. So I didn't just do ZFS send greater than dev null, which is even faster, but I wanted to capture the performance of sending out to the pipe because due to some previous investigations, we suspected that there might be problems there. I used DD. Quick side note, there are not a lot of utilities, standard Unix utilities, that can produce or consume a pipe at more than 1 GB per second. I tried using PV, the pipe viewer, initially, and that will instantly become the bottleneck of any pipe. So don't do that. For the test setup, I didn't use compression, and I didn't use record size 8K. Instead, I set the record size to match the compressed block size that we typically see of around 4K. And I just have 100 gigabytes of data. When you're doing ZFS send, basically what that's doing is like issuing a whole bunch of reads to disk, and then they're completing, and then we're generating the send stream. When we have a lot of IOs, a lot of reads pending in the ZFS VDEV queue layer, then ZFS is able to do aggregation. So when we're going to issue an IO, if we see, oh, there's actually several adjacent IOs to this that are all also reads, then ZFS will issue one big read to the disk and then copy out the data wherever it needs to go. The problem with this is that it can lead to really inconsistent performance because whether you get that IO aggregation or not depends on it depends on like the timing of everything that's happening. So you might get into a mode where it's like we're just the IOs are flying out really fast and we're not getting any aggregation, and you might get into a mode where things are getting queued, and it also depends on the layout of the data on disk. So I disabled this read IO aggregation for my test so that we get a consistent per IO cost. So every 4K, we're actually sending down through the block device driver down to the actual hardware. This also simulates what you would get in kind of a worst case scenario where the files are spread totally evenly across your disk and super fragmented. So the test environment, I used Ubuntu. The one thing that I needed to do is on the later Ubuntu releases, they've changed the default init on alloc. This is a new feature in the Linux kernel 5.0. In Ubuntu, they said, like, for security reasons, whenever you allocate a page, we're gonna zero it out. That leads to pretty poor performance for ZFS when you're at high throughputs. And so we've actually disabled this in our product, and you'd want to disable it for high throughput workloads. All right, so let's get started with our investigation. So let's start with ZFS send. Let's start with the flame graph. So this is a flame graph. What it's telling us is kind of on you have a bunch of these bricks, right? So like here's a stack of bricks, and the stack of bricks is telling us a stack trace. So for example, here like ZIO execute called ZIO VDEV IO done, which is called VDEV Q IO whatever. And the width of each brick is how long that function was on CPU, or that function or its callees were on CPU. So we know that like, ZIO execute was on CPU for longer than ZFS do send, for example. But this is kind of a lot to look at. Usually you can view this interactively and kind of zoom in on different parts. I'll kind of summarize this for you. So about half of our CPU is idle. So that's interesting. I don't know, maybe we don't have a CPU problem. Why do we have all this idle CPU? most of the CPU that is being used is by these ZIO threads. And there's a whole bunch of these ZIO threads, at least as many as there are CPUs. So at least in theory, if these threads need to do more work, then they should be able to consume the idle CPU. And so these threads shouldn't be the bottleneck. And then let's look over here. So we have the main ZFS thread. So this is like the thread that's running from userland. It's outputting data to your pipe, and it's on CPU 73% of the time. We also have this other thread, send prefetch thread, which is on CPU also about 3/4 of the time. So you notice that I said it's on CPU for 3/4 of the time, but it's not consuming 3/4 of all CPU. So for each of these threads where there's just one thread, it can only be on one CPU at most. So the way that we read this is, for example, we can look at this function here, archheader_alloc. It says it's on CPU 1.7% of the time. So we have to multiply that by our 8 number of CPUs to tell us that this function is on the one CPU that it could be on for 13% of the time. So that's interesting. Let's try and figure out what this prefetch thread is doing and how it kind of fits into the flow of data with ZFS send. So this is a diagram showing each of the threads that's involved with the ZFS send, and then what data is being sent I shouldn't say send. What data is being passed from one thread to the next. So this traverse thread is walking the tree of blocks and figuring out what blocks we need to send. For a full send, that's just all of the blocks that are part of the file system. And it's outputting the block pointers that we need to send. So it's just the block pointers. We don't actually have the data yet, but it's telling us which blocks we're going to need to retrieve from disk in order to send it. Then we have the prefetch thread, which is what we were looking at previously. And what it's doing is issuing an arc read. So it's telling the arc, hey, go off and read this data. It's not actually waiting for that to complete. We're just kicking it off. And we aren't actually getting the resulting data. We're just prefetching it so that it'll be in the arc for a later real read. And then we have the ZIO threads, which have many little squiggly threads here, which are going to actually issue the reads to the device driver and then notify anybody who's waiting. So the prefetch thread is passing on this exact same list of block pointers that we need to send to the main thread. So the main thread is going to now issue a real read to the arc, which hopefully it's already cached, and we're just getting the cached data. And then it's going to output the data to the pipe, which is going to be consumed by DD. So there's already a couple things that we can see might be issues here. One is like we're doing an arc read here, and then we're doing another arc read here. Maybe we could just do one arc read and have this thread like pass the actual data on. That would probably save us some CPU in the main thread. Probably wouldn't help with the prefetch thread. But the other thing, I should also mention, so we're doing all these arc reads, we're getting all the data into the arc cache. Eventually that data is going to have to be evicted. So there's another thread, the arc evict thread, which we also saw in the flame graph over here, which is going to have to remove that data from the arc to make room for the new blocks that we're reading in. All right, so pause for just a sec. What's so special about this workload? So we already mentioned that we're using small record size, we have small compressed block sizes. The second big thing is that this is single threaded. I know that there's a lot of threads on here, but because every block needs to be processed by every one of these single threads, so any one of these threads can become a bottleneck. So if the prefetch thread is taking a long time to do its thing before it can pass the block pointer onto the next thread, then it can become essentially the single thread that is our bottleneck. Yeah, so as I said, there's several threads, but each one is just doing one job, and each one has to process all of the blocks. We're doing a lot of work with the ARC and the DMU around debuffs. Those subsystems are pretty scalable, but they're relatively heavyweight. There's a relatively high latency for each I/O. You can get really good throughput from ZFS if you have a lot of threads hitting it at the same time, but it's not great for single-threaded throughput. And this is true not just for send and receive, but like if you're just doing like a single DD to read or to write, you're going to see the same kind of curve relative to the record size property here. So we're going to see two kinds of solutions throughout this talk. One is just don't do that, bypassing the ARC and the DMU altogether. And the other is batching operations together. So even though we need to issue an IO for every block, we can recruit a lot of threads to help us with processing those IOs, so we can get good scalability there. But there's other things where we're processing things one block at a time that we can improve on by batching those operations together. All right. So this is what we have now, and how can we fix it? So the change that I made was to change this prefetch thread into, I now call it a reader thread. And what it's going to do is issue a ZIO read. So we're not going to add anything to the ARC. We're just going to go directly to the ZIO layer, read that block, and then pass or initiate the read and pass that ZIO on to the next thread. We're going to check if it's in the ARC first, so that in case it's cached, it's probably not cached, but just in case you have a workload where it is cached in the ARC, we'll check if it's in the ARC, but that's a lot faster than adding something to the ARC because we don't have to allocate any new data structures, link them into our hash tables, et cetera, et cetera. Then the main thread doesn't need to issue any IOs, doesn't need to talk to the ARC at all. It just needs to wait for that ZIO to complete, and then it can produce the stream data. So this is a great idea. Let's see how it turned out in practice. So usually what I would do is look at the flame graph and see, okay, did I reduce that CPU time that I was targeting? In this case, we did. So allocating the ABD, the ARC buff, allocating the ABD is takes much less time, 3% of the CPU time than we took to allocate the ARC header, which is 13%. And then checking the ZFS send throughput, we did get a really good improvement here, 36% better on our 4K target block size. Cool, so let's look at another thing. 36% didn't get us quite as far as we want to go, so let's see what else we can do. So I wanted to talk a little bit about how I used off CPU flame graphs. So if we take a look at the send prefetch thread that we were seeing before, where we saw it was using a bunch of CPU, what was it doing when it was not using CPU? So by using an off CPU flame graph, we see the same stack of function calls, but this time the width is telling us how long this thread was blocked, not on CPU, because we were waiting on the stack trace. So in this case, we were waiting on a condition variable in BQ NQ. And what this is doing is waiting for, it's trying to produce its output, trying to queue it on the queue of output, and it isn't able to because the queue is full. It's waiting for the next thread, the main thread, to consume the output. So the way that we figure out how important this is we ignore this percentage here, and we instead look at the number of samples, which in this case is the number of microseconds. So this is telling us that for 2.5 seconds, 2.5 seconds, we were waiting on the stack. We divide that by our sample time. So I was running this data gathering for 10 seconds, and it tells me that we were off CPU for 25% of the time. We can then look over to the main send thread. I wonder what, it's on CPU a bunch of the time. It's also off CPU. What was it doing when it was off CPU? So it spent a bunch of time, 14% of its time, waiting for locks and CVs associated with the pipe. So we're trying to output to the pipe, and we're having to wait either on the mutex or because the pipe is full. Taking a look at the code, I found that we're calling pipe rate 2 times for every block, which means that we need to do this every 3 microseconds to get the performance that we're targeting, which is pretty often to be scheduling and waking up other threads. So how do we address this? So this is the same diagram that we saw before. with our reader thread, the main thread, passing the stream data block at a time over to DD. So what I did was I introduced a new thread. So I'm sending it block at a time, but now I have a new thread, this writer thread, which is consuming the data. What the writer thread is going to do is batch up the stream into 1 meg chunks and write those chunks 1 meg at a time to the output stream, to the pipe. So the end result is we have 1/500th of the number of calls to the pipe, potentially 1/500th of the calls to the mutex, and having to potentially go to sleep and wake up the DD thread. The other cool thing about this, by introducing a new thread, is that the main thread can continue working while the writer waits on the consumer. So in the real world, we aren't just like doing DD to dev null. We're sending out over the network. The network might have packet loss. It might have kind of intermittent or bursty throughput. And this allows us to keep the main thread busy while the writer is waiting for that packet loss to be recovered from, or waiting for the network burstiness to kind of go back to full bandwidth. Cool. So I did a few more little kind of micro improvements, like taking locks less often and things like that. Got a little bit more from that. And overall, I was able to get a 87% performance improvement, bringing us up to 840 megabytes per second, which beats our goal of 5 gigabits. But all that's kind of for naught if we're still piping it through over to slow ZFS receive, because we can only produce data as fast as it can be consumed. So all we've done so far is like reduce the CPU usage on our sending system, but we can't actually get the job done any faster. So let's take a look at ZFS receive. Again, let's start with the flame graph. Summarize it here again. It looks kind of similar. A bunch of idle time, bunch of time being in the ZIO threads. And then we have this receive writer, which is 2/3 on CPU. That's just a single thread, and then the main thread, which is more than half on CPU. So let's drill down on that receive writer thread. Here I'm displaying the on CPU and off CPU flame graphs kind of next to each other with their widths proportional to the amount of time that we were spending on CPU and off CPU. And actually in both the on and off CPU cases, we see that we have kind of two big categories. One is dealing with debuffs, which is kind of the heart of the DMU. These are in-memory data structures that represent each block. And then the other big chunk is dealing with transactions. So whenever we're making doing a write or making a change, we need to have a DMU transaction that manages that write. And then off CPU, we're basically dealing with waiting for locks associated with those two data structures. All right, so what are these debuffs? Why are we creating them? What are we doing with them? So let's take a look at here. This diagram is going to be showing the in-memory data structures that are involved in ZFS receive, which is very similar to what you see with any writes in ZFS. So what we really care about is our data. In this case, databases don't make very good pictures. So in this case, our data is a JPEG of some pre-pandemic well-dressed coworkers. And we have the arcbuff, which keeps track of that. And the arcbuff is associated with an arc header. So the main thread is going to get the data from the stream and put it into this arcbuff. Then we're going to, now we need to associate that with, like, that belongs at this offset of this file. The debuff tracks what is at given offsets of files. So that we create this debuff. Everything in ZFS on disk is a tree of blocks. So you have like the object points to blocks that are called indirect blocks, each of which has a bunch of block pointers that point to maybe more indirect blocks, which point to eventually to the actual data. So whenever we have the leaf debuff, the one that actually contains the user data, instantiated in memory, we also have the indirect debuff, all the indirect debuffs above it, and the dnode, which is what tracks this file. Now, we mark the debuff as dirty. When we do that, we create this thing called a dirty record that keeps track of all the dirty data. And we do that so that the sync thread can find all the dirty data that it needs to write out. So the whole point of all of this green and blue stuff is so that the sync thread, which processes syncing out TXGs, can create an IO that points to our data and write it out. And then obviously we need to, after we write it out, we're going to get a block pointer and we need to stick it into our indirect block. And then eventually the write's going to complete. We then we'll get rid of the dirty records, link the ARC header into the ARC cache hash table, and eventually we're going to have to evict that stuff to make room for more dirty data. Yeah, I know there's a lot of stuff. If you take anything away from that, you should take away that. It's a lot. There's a lot of things here, and there's a lot of things pointing to other things. And each one of these is relatively heavyweight. So like the dnode, it's not just like one pointer to one leaf debuff. It's like a whole data structure, AVL tree that points to all of them. So every time we're like instantiating a new leaf debuff, we have to associate it with each of these, which means like getting a lock associated with it, adding it to a data structure, which is probably like O of log n. So these are relatively heavyweight. And that's not even the worst of it. So for every one indirect debuff, it can point to 1,000 data blocks, which I've shown just a few of on the slide. So you really have pointers and pointers going everywhere, lots of space accounting to know how much memory we're using. So what can we do about it? Let's get rid of the stuff that we don't need. So what I've done is introduce something called a lightweight write, which I'll try not to say too many times quickly in a row. So we have this new type of dirty record that's a lightweight write dirty record, and it is not associated with any debuff. Instead, it just says, here's the data that we need to write to this object and this offset. So now when we're writing out all the data in syncing context, we're going to follow these pointers down to the indirect debuffs dirty record, and then it has a list of of dirty records of the leaves, and we're going to be able to create this ZIO that points to it. And because of this, we don't need to create the leaf debuff. We don't need to create the arc buff. We don't need to link it into the ARC hash table. We don't need to evict it later on. So this is great. The downside is this is like, it's really slick. It's really lightweight, but we can't handle reads from data that's lightweight dirty, because the way that we find, like if you're doing a read, we're going to find the debuff associated with that. If it's not there, then we're going to instantiate it. There is no debuff associated with this data. So if we kind of just try to drive on without making any additional code changes, we would just instantiate it. We wouldn't find this dirty data. We'd instantiate a new one, read it from disk, and then we would see the wrong data. We would see what's on disk rather than what was written but not yet synced to disk. So if you're wondering, this is why I removed the dedupe receive code. I know we talked about doing that I think that was proposed at this conference like 4 or 5 years ago. I finally got around to doing it because I didn't want to deal with this. So now that that's been removed, ZFS Receive doesn't ever read from the dirty data. It's a write-only workload until the receive completes. So we don't need to worry about that. The other implication of this is that the receive data doesn't pollute the ARC. So because we're not putting it into the ARC, it is not cached in the ARC. You won't get a cache hit from it. But for this data, it's typically not. You're not going to typically get cache hits. You're not going to typically be reading from it right after you receive it, especially not if you're receiving a lot of data. It's going to be falling out of your cache anyways, besides before the receive completes. So how did this impact performance? This is what we had before, 30% of our CPU dealing with debuffs. And this is what we have after, down to 13%. And we have similar improvement in time waiting for locks. So that's great. And running the ZFS Receive, we got a 54% performance improvement. So awesome. What else can we do? So let's take a look at, again, in the Receive writer, we saw the other big category of CPU usage was dealing with transactions. So for every block, in this case, every 4 kilobytes, we're creating a new transaction. And that's having to like look up the dnode, do a bunch of accounting, make sure that you have enough space to do it, and we're doing that every single 4 kilobytes. And what I noticed is that you know, if you have a big send stream, it's probably mostly in big files, especially if you have small record size. You probably have a lot of records there in each file. So we have a lot of write operations that are happening to the same file. And most of these things are finding the same, like finding which file we're writing to. Let's batch that up. So what I did is batch up contiguous write operations. So when the send stream, we see, write to offset 1, write to offset 2, write to offset 3. What I'm doing is just remembering that, not sending those to the DMU yet until I get a whole megabyte of those write operations, and then sending that to the DMU with one transaction. So we had a huge reduction in the amount of CPU used dealing with those. So down to actually was less than 1% of one CPU. And we got a good additional 11% performance improvement on top of what we already had. Cool, so let's take another review of receive CPU usage. This is what we had as the baseline. After we implemented those 2 improvements, the receive writer is using a lot less CPU. We totally got rid of this debuff evict. The other threads are mostly using more CPU because we're going faster and we haven't done anything to improve them. And the main thread is still sitting here at 57% on CPU. So let's take a look at the flame graph for the main thread. 20% of it is dealing with pipe mutexes and condition variables. So we have kind of the same situation as we did with the send case, where we're doing 2 calls into the pipe for every block. So again, what I did was batch up the pipe read calls so that I'm reading 1 megabyte at a time, which had a huge reduction in the amount of CPU used from 20% down to 4%. Although my native implementation needed to do an additional B copy, that cost 10%. Still, we're better than we were before at 20%, and got an additional 12% performance improvement on the ZFS receive. But, so the way that pipes work, each side, one side reads and the other side writes. And the side that's reading, it only reads. You can't push things back into the pipe. So the problem is that when we're reading the last chunk of the send stream, we don't know that it's going to be the last chunk a priori. So we read in that whole megabyte. And if there was some data after the end of the send stream, we're going to be reading that in as well. There's no way to undo it and push back in the part that we didn't actually want. So this breaks things where the send stream is followed by some other piece of data, like with ZFS send capital R, or capital I, where we're generating a bundle of a whole bunch of different snapshots. So to really address this, we probably need to change the send stream over the wire format. So I didn't do that, but this kind of proves out how much performance benefit we could get if we could make this real. All right, so in conclusion, this is the baseline where we were before any of these changes, and then here is where we improved performance. We actually got a pretty good performance boost even with the large block sizes, but almost doubling performance, 87 or 90%, up to 840 and 740 megabytes per second. So where are we at with these changes? So the bypassing the ARC and the write transaction batching are done, and those will be in OpenZFS 2.0. The other changes, the batch output and lightweight write code is basically done. I'm still working on upstreaming that, and then the batch input needs a little bit more work. I see we're running short on time, so I will skip the future work. You can come to the breakout session if you want to hear more about other crazy ideas, but I will go to Q&A. All right, so Jan asked, does ZFS support reading and writing TCP sockets within kernel TLS? So the way that it works, ZFS send and receive are passed a file descriptor from userland. So yeah, you can attach that file descriptor to that can represent a socket. I haven't done that in practice. that'd be something really cool to investigate. What we're doing is sending to a pipe to a userland process, which is then doing like a whole bunch of other stuff, encryption, and spreading it out over like a whole bunch of TCP connections to get really good bandwidth. So ZFS supports it. I don't know how widely used that is. Maybe if folks have experience with that, then come to my breakout session and let's talk about it. Jan also asked, what's the definition of idle CPU? I'm not sure that I understand that there are different definitions, so maybe you can help educate me on that. I was looking at both the flame graph where I'm gathering all of the stacks and not excluding the idle ones, and that lined up pretty well with, top or iostat-x, something that just gives you a summary of like this percent CPU was system, this percent was idle. Someone asked what kind of load this was run with. So there was no load beyond the send or receive that I was testing. And I talked a little bit about the test setup and methodology here. So like when I'm talking about the send performance, it's just like, it's literally running the CFS send, then the snapshot. So we're doing a full send, not an incremental, and then piping that into DD with the block size of 1 megabyte. So DD is going to be consuming it in 1 meg chunks. Okay, so Anonymous is asking about the readability of the libzfs send receive.c code file. I think all of these changes that I've talked about here do not touch libzfs. These are all kernel changes. I did do a bunch of cleanup that's in like smaller minor commits that are already in there to the kernel send and receive code. But I did not have to touch the userland stuff. I was thankful to not touch it because you are correct. It is not very easy to understand. Yeah, that's still as it ever was. All right, and I don't see any more questions. Awesome. All right, thank you.